Now let's continue our discussion about time series by looking at autocorrelation, white noise, and forecasting. So first, let's start with forecasting. Here we're looking at the gambler's fallacy. That's, when you think that because something happened before or more frequently before than normal in the past, it's going to balance out and happen less frequently in the future. So if we had the example of rolling a snake eyes or two ones 2 times in a row, having the thought that you're less likely to roll it again in the future, or the idea of landing on a red colored number 8 times in a row in a roulette wheel, thinking that, that means that the black number is more likely to spin next time. Now, can you forecast the next roll of the dice based on previous rolls? We know that answer to be no, particularly from our prior discussions on probability in earlier statistics course. But now we're going to look at the same problem here within the context of a time series analysis. But before we do that, let's start talking about autocorrelation. So autocorrelation is where you have your observation at y sub t. It's going to be correlated with your prior observation, so at y sub t minus 1. And so here we have a time series at time t is y of t equals y sub t. And then your first lag would be yt minus 1 equals y at t minus 1. So this is going to be a plot of a time series with autocorrelation, and we'll do it a little bit again and talk about exactly what it means. But overall, when you have autocorrelation, it means that your current observation is really dependent on that prior observation. A pretty classical example of that would be stock prices, where we're looking at today's stock prices being highly correlated with yesterday's stock price. So let's look at the scatter plot for autocorrelation. Autocorrelation, once again, is that correlation of your present values to your lag values. So in this case, we're looking at a couple of graphs here where on the x-axis we have the value from the last roll of the die, and then on the y-axis we have the current die roll result, excuse me. On the right, we have a different data set that looks at the kilowatt hours generated, so that the energy being produced in kilowatts for the lag versus the current. Autocorrelation between the present value and the first lag value is called your first order autocorrelation. And so when we look at these two scatter plots here, we see that there's really not any pattern for the roll of the die. So we can see here that there's just complete random noise, and there's really not a pattern that we can discern from the scatter plots. On the other hand, when we look at the plot for the lag of the energy production in kilowatts versus the current amount generated, we see that there is a linear relationship here. So we can determine that there is a dependency on the current energy usage due to a correlation to our prior energy demand. And we can visualize this using an autocorrelation plot. It will allow us to see the autocorrelation and our multiple lags. The blue ranges indicate a 95% confidence interval for each lag. And what that means is if the bar exceeds this 95% confidence interval, that indicates that there is autocorrelation occurring. Now on the left, where we have the die roll, we see that nothing is piercing that 95% confidence interval band. But on the right, we see that for the kilowatt hours generated, that there is autocorrelation in our data set because we are piercing that 95% confidence band. So now let's look at a white noise series. A white noise series has the following characteristics. It varies randomly around its mean. In this case here, it can be 0. It does not have any systematic variation. It consists of only random variation and has constant variance. To look at autocorrelation gain for die roll that we did before in that series, there wasn't any type of pattern, and we would see that there's just complete random noise. And so that would be a white noise series, just like what we saw before. This is that white noise scatter plot that it would look like. It wouldn't have a pattern, and we would look at the autocorrelation plot, and we see that none of them pierce that 95% confidence interval. There is actually a test that we can perform to assess whether or not the series itself is a white noise series. That's called the Elgin-Box chi-square test for white noise. And again, a white noise time series is a Gaussian time series. And what that means is it has a normal bell shape with a mean of 0 and a positive fixed variance with all the observations independent of each other. The hypothesis is that the series is white noise, and the alternative hypothesis is that one or more of the correlations of lag M are not zero. Basically, that there is autocorrelation. So the null hypothesis is that there's not any autocorrelation, which means that the series is white noise. The alternative is that the series is not white noise, which means that there is some autocorrelation. And note that this test can be applied to the original series or the residuals after you have fit your model. So now let's transition to talking about forecasting and accuracy assessments. You know, if someone asks you whether you can forecast something, your answer should be yes. But the bigger thing is, you know, whatever kind of forecast you want, but you really worry more about the accuracy of it. So the question you should be asking yourself is, do you stake your reputation on the accuracy of the forecast? Your answer should be no. But you could stake your reputation on the methodology that was used to generate the forecast. That is, you may not have control over the data accuracy and the validity issues that may affect your forecast. So, for example, is modeling the volume sold an accurate representation of the true demand? So you're making an assumption that the volume sold is a representation of the treatment. But what if there's some porting going on, or there was a hurricane that passed through which, you know, led a spike in the purchase of bottled water, or some other event that resulted in some effect that might have a one-time effect on your true demand? You know, you may not be able to pick up on that on a time series itself. You know, were there shortages in supply chain that you weren't aware of that could hurt your forecast? Perhaps there wasn't enough raw materials to produce the goods in a given time period that affected your overall values. So there's always going to be some elements that you cannot control that will affect your data accuracy as well as your validity. Ultimately, what we need to do is assume that the underlying future behavior remains consistent with past behavior. If we cannot assume that, then the forecast we generate is not going to be useful. However, you don't have any control over future events that might affect future behaviors, such as catastrophes, economic downturns, war, integrity of the players, survival of key players, and so on. You know, maybe even a pandemic, right? All of these things will affect the overall time series forecast that you make, and these are things that are going to be outside of your control. So now let's talk about how we're going to do the validation for a time series analysis. Ultimately, we are trying to forecast some future occurrence. In this example, we're trying to forecast a future demand. So say we want to forecast the next 4 quarters of sales, and we have the given data set that goes back a few years or more. We're going to forecast the observed values with a set of observations. We're going to section off a holdout sample, and that typically should be, you know, if we're looking at quarters, at least 4 quarters of data that we're going to use to validate our fitted model. And again, in this case, typically the holdout sample would be the most current observations that we have. So in this case, we're looking at quarterly data. So that would be the holdout of 4 observations with the 4 most recent quarters. And then again, we would ultimately try to predict the next 4 quarters, which is once again our goal of a time series analysis. Now let's look at an example of how this would work. So we're going to divide a time series into 2 segments. There's going to be the fit sample, which we use to train our forecast model, and then there will be a holdout sample that's used to evaluate the accuracy. We're going to derive a set of candidate models, and so we'll go more in depth about these in other presentation. But these candidate models can be exponential smoothing, ARMA, or an ARIMA model. And then we're going to calculate the accuracy of our model using whichever accuracy statistic we've chosen to use by using the fit sample to the forecast on the holdout sample. So, for example, our last example, we had 4 quarters that were going to be in our holdout sample. And so you would use the model that we developed on that holdout sample. Then we're going to choose the model with the best accuracy statistic on the holdout sample, not on our training sample, as we've talked about before. And then finally, we will use the best model to generate the forecast for n number of future periods. So n can be any number of periods. Obviously, the further out you go in the future, the higher the uncertainty is going to be for those predictions. So choosing the holdout sample, you want to choose enough points to account for a complete seasonal period. So, if you're looking at monthly data, you want to have at least 12 observations in your holdout set. Or looking at quarterly data as we were before, then you want to have at least 4. The holdout sample is always going to be at the end of your time series. So we need to make sure that we're always using the most current data that we have. And if we have some kind of unique behavior occurring within our holdout sample, you should not use a holdout sample. Instead, you're going to use the entire series to complete the accuracy calculations. So if there's something funny going on with your current observations, then you really can't use the most current observations since they're not going to be representative of your overall sample. So here you would want to base your accuracy calculations based on the entire series and not using that holdout data set. And if you have insufficient data to split your data into fit and holdout samples, then you want to base your accuracy calculations on the entire time series. So ultimately, if we have a very small sample size, that's going to prevent us from creating a training data set and a holdout test set. So in that case, we would just use all of our observations. As a reminder, we're going to fit the sample, that is the training data set, to estimate the model parameters for the accuracy evaluation. This is going to be used to forecast the holdout sample that we have. Again, that holdout sample should be the most current observations. This is going to be used to validate the model accuracy, and it's going to assimilate a retrospective study, meaning we're going to use this to see how well it generalizes to new observations. Once we are satisfied that the model will in fact generalize and is performing well, then we will use that full sample, and that is the fit and the holdout data to fit that final model, which is what we end up deploying. When preparing a time series model for forecasting, there are a few rules of thumb to keep in mind. So you want to have at least 4 points for every parameter that you have estimated in your model. Anything above the minimum series length can be used to create that holdout sample. So once we've sufficed these criteria, anything that you have left over can then be used for your holdout sample set if you so choose. And again, at a minimum, we should cover a full season. So if we're looking at monthly data, we have a minimum of 12, quarterly data, a minimum of 4. And then holdout samples should rarely contain more than 25% of the series. So we wouldn't want to have, more than 25% in that holdout. Now let's look at model fit statistics. These are the ones that we've talked about before, but as a reminder, we can always use the mean absolute percent error. We can use the mean absolute error. You can look at the R-squared. We can look at the root mean squared error. In this case, let's look at an example here for the mean absolute percent error and the mean absolute error. So here we have our holdout sample, our observed true values, our forecasted values, and then the residual is the difference between the two. So we can take the absolute value of the difference here, the mean absolute error, which in this case is our actual minus our fit, divided by our actual value. And so in this case, the first observation is off by about 3.8% or 0.038. And then we have these values, plugged into the formula that you saw in the previous slides. So now let's talk about the necessary conditions for a good forecast. First, you need the identified signal needs to continue to the future. That is, what happened in the past needs to be likely to happen in the future. So whatever trends we are seeing or any type of signal that we're picking up on is going to persist in the future. The forecast model complexity should be adequate to capture the signal components. The forecasting model should not be overly complex. We've talked about this before as well. Just like our other models that we have discussed, time series models can get pretty creative in the level of complexity that we can add, and as we'll see in some of our later discussions. So we should always be biased to keep it as simple as possible, but not any simpler than that. So we'll again visit some different models we can apply, and we should always be biased towards keeping a simpler model. And the best model forecast is the one that captures and extrapolates the most signal while also ignoring the noise. So in choosing the best set of forecasts, a good forecast should be highly correlated with the actual time series. It should exhibit small forecast errors, and it should capture the prominent features of the original time series. In addition, the assessment of the forecast quality should be based on the business, engineering, or scientific problem that you are addressing with this model. So again, you always want to bring that actual business element that you're going to dictate whether or not that forecast is actually effective in achieving the purpose of the problem that you're working on.